for the interrupt. So this was at the CFN at Brookhaven National Lab. So first, let's look at the most of the metals we use commonly is the metal is in the polycrystal form, where the different grain have different orientation. So the grain boundary existing as a result of the misorientation between this grain and its neighboring grain. So the grain size is normally in the micron size. For example, in this picture, we see that the grain size is average is about 100 micron. So then there's a lot of atoms located in the grain interior rather than in grain boundary. This even down to the ultra-fine grain, which is about 250 nanometer to micron size. But when we refine the grain size down to the nanometer region, which is below 100 nanometer, then we start to find out that the grain interior volume fraction start to decrease, while its grain boundary starting to increase. And when we refine the material into the finest grain size, which is about 5 to 10 nanometer, we see that the grain boundary's volume fraction even surpass the grain interior's interfaction, grain's volume fraction. This might signify significant change of the material's property. So then let's look at the empirical Hall patch law. So the increase of the yield strength scales with the inverse, scales with the increase of the square root of the grain size, or decreasing grain size. So when we refine the material down to the nanometer region, then exceptional high strength would be expected. Indeed, the experimental data shows that when we refine the grain size, exceptional high strength like 3 GPa hardness and 2.5 GPa tensile yield strength has been achieved. So what's the reason for this on the nanoscaling scale strengthening? So we know that with the smaller grain size, we have more grain boundaries. So the dislocation moving across the grain boundary becoming harder. And there's going to be a dislocation pile up at the grain boundary and causing the strain concentration. And this strain concentration will lead to further hinder of the dislocation.
What exactly is the yield strength?
The yield strength is the criterion that tells whether the material is going to plastic deform rather than elastic deform.
Okay, so there is a threshold.
What? Yeah, there's a threshold. Yeah, there's a criterion for that. Usually we use the the slope, which is actually the Young's modulus, and we just move a 0.2% strain and measure that yield strain in the stress rate curve.
For transition between plastic
and elastic, yeah. Okay. So then, with the further refinement of the grain size down to the 10 to 20 nanometer grain size, the strength start to plateau. And even some results shows that it's decreased at the finest grain size. This phenomenon is termed the Hall patch breakdown. And the Hall patch breakdown signifies a shift in the deformation mode from the dislocation-dominated plasticity comes to the grain boundary-mediate deformation process. And you know, with this small grain, even like 5 to 10 nanometers, it's really hard to study using a conventional experimental method such as TEM. Then the simulation play a crucial role in understanding what's happening for this material in the deformation. So the formal work shows that the dislocation can emit from the grain boundary or triple junction and being absorbed by the grain boundary. And also the grain boundary can sliding, and also atom shuffling has been observed right here. And grain boundary can also migrating with during the deformation. All this shows that its Hall patch and its breakdown introduced a scale law for the nanocrystalline material. Then, so even though we achieved high strength of the material through nanostructuring the material, then we however, it has a negative implication for the ductility, such as the experimental data shows that most of the nanocrystalline metals shows only like no more like few percent elongation to failure. Why is coarse grain counterpart like micron copper, it can reach as high as 60% elongation to failure during the uniaxial tensile testing. So the reason for this poor ductility, the people are saying that there are three mechanics have been proposed to explain this poor ductility. First is lack of the available strain accommodation process. The second is the permeatual flow because of the processing introduced force, and last is the string hardening capability. So if we are able to provide the string to be accommodated in the nanocrystalline material, we might improve the tensile ductility of the material.
These are experimental results.
Yeah, experimental results. So with the extreme refinement of the grain size, we approach the amorphous limit. Well, the atom shows no long-range order. And now this amorphous solid, we call it metallic glasses. And one of the most attractive property of metallic glasses is extremely high strength. According to this experimental data, it says the shear strength as high as 2 GPa can be obtained. However, according to the theoretical calculation, that the shear strength of the metallic glasses can reach 0.1 G, which G is its shear modulus. However, through studying the 30 different metallic glasses, the Johnson concluded that the experimental obtained shear strength of the metallic glasses is only about 2.026 G, which is 3 to 4 times smaller than the theoretical value. So what's happening in this material? It's because of the shear banding forming. And first, let's look at how the atoms plastic deformed in the metallic glasses. It takes form of the shear transformation zone where a group of atoms cooperatively rearrange themselves over a small distance, overcome its potential landscape. And then, during the deformation, a lot of these shear STZs being confined in a narrow area, we form this shear banding, such as shown in this TEM picture. And this shear banding accommodates most of the strain during the deformation and leads to the catastrophic failure of metallic glasses. Then we know that metallic glasses and the nanocrystalline metals both has high strength, but both of them suffer from the poor ductility. However, when we combine these two materials to form a crystalline-amorphous nanolaminate structure, exceptional mechanical property has been achieved. So one example is given by Wong. At 2007, they used the magnetron sputtering fabrication to alternatively patent a nanocrystalline copper layer with copper zirconia amorphous layer to form this crystalline-amorphous nanolaminate structure. Well, the side view of the TEM picture shows that the nanocrystalline layer has a columnar grain shape, right in here. And it has a layer thickness of about 35 nanometer. While the planar view shows that the average grain size is also about 35 nanometer grain size. And the amorphous layer is about 5 to 10 nanometers. And when under the uniaxial tensile loading of the material, it can reach as high as 1 GPa strength. And it has improved tensile ductility with the total elongation up to 13.8%. And the stress strain curve shows a perfect elastic plastic behavior with zero string hardening. So what's happening in this material? In order to study the deformation mechanics about the nanolaminate structure, they used the simulation, the molecular dynamics simulation. Well, they built this single crystal nanolaminate. Well, it has a single crystalline copper layer about 10 nanometer. And then it has amorphous layer about 5 nanometer. And this is actually 2.5, but because of the periodical boundary, it's actually make it 5. And the uniaxial tensile loading is applied in the 112 direction. And then the result shows that the dislocation can be emitted from the lower amorphous crystalline interfaces and being absorbed by the upper amorphous crystalline interfaces. And if we visualize through the Von Mises shear strain, it shows that the incoming dislocation can trigger the STZs in amorphous layer, and with more dislocation, there are more STZs in amorphous layer. However, we don't observe any shell bending forming. So all the results shows that the amorphous crystalline interfaces can act both as a source and a sink for the dislocations. So what's the object of today's research? First is to resolve the mechanics operating in a nanolaminate containing the columnar nanograins. So if we look at one structure, one important structural factor is missing, which is grain boundary. And we all know that grain boundary play a crucial role in the deformation of the nanocrystalline material. The second is to quantify the STZ dislocation coupling and its implication for the global plasticity. And the last is to understand the deformation process response for the superior ductility of the nanonap when we compare it to the EQX nanocrystalline copper, where it has the random orientations and in the EQX form. So the unique structure built in this study is the columnar nanolaminate. It has the same layer configuration as the single crystal nanolaminate. However, we introduced the grain boundary in the crystalline layer, as shown in the inset of this picture, which is the plan view of the columnar nanolaminate. It has a voidal tessellation with the average with 25 grains and the average grain size of 10 nanometers. And then here is the relaxation and deformation conditions, and we use the common neighbor analysis to characterize these atoms, such as the face-centered cubic atoms is the green atoms, and the hexagonal close-packed atoms is the red atoms, and the grain boundary atoms and amorphous atoms are the gray atoms. So then, in order to study the deformation history of this material, we use the slit vector analysis. So the advantage of use this technology is that this value can directly correlate to the certain atoms' Burgers vector, such as for copper atoms, its partial dislocation is about 1.47 Armstrong, and the full dislocation is about 2.55 Armstrong. And we compare these two, actually it's the same snapshot. But through the slit vector, we can show the full dislocation glide plane, while this is no. We cannot see from anything from this. And then, first, let's look at the mechanical response of the different structure. First, if we compare the red one is the columnar nanolaminate stress-strain curve, and the blue one is the single crystal nanolaminate stress-strain curve, and the black one is EQX nanocrystalline copper. So the columnar one compared to the single crystal one, this is more stable, and it experienced a small strain hardening after yielding, and then it shifts to the strain softening at a 6% strain, while the single crystalline experienced several abrupt strain drop, and this is believed correlated to the dislocation, emission, and absorption. And when we compare the EQX nanocrystalline copper structure stress rate curve with the columnar one, it looks like it's really similar, but it's just a little bit different deviation here. However, later results will show that the strain being accommodated in these two structures is significantly different. Then we output some snapshots from the structure to study its deformation mechanics. First, let's look at the 3.2 strain. We see that there's a leading partial being emitted from the grain boundary and amorphous crystalline interfaces intersection, where the atoms shows a higher level of slit vector value, or the higher level of the plastic deform. And then this leading partial was removed by a trailing partial, and it leads to a full dislocation glide. And this full dislocation being absorbed by the lower amorphous crystalline interfaces and trigger more shear transmission zones in this lower amorphous layer, which leads to another dislocation trouble upward. And also, in the neighboring grain, we see the deformation twin found in here. And when we compare
How exactly epsilon is defined?
what?
How exactly epsilon is defined? What is epsilon? Epsilon.
E. A strain. It's a 10 point.
So yeah, how is it differs in that picture where it is 10.8 and the one that is 3.2?
Yeah.
How does it differ?
So when we do the simulation, we set the total time step. We set a step which is about 2 femtosecond, right?
2 femtosecond.
Femtosecond, yeah. And then we run a certain steps and set the strain rate. There's a command in the lamps which is setting the deform, and you can set a strain rate, and you then we deform the certain time it can reach the certain. We can calculate from the time step and calculate the strain.
You use lamps.
Yeah.
Lamps or lamps?
Lamps. M-A-M-S. Yeah. Sorry. So when we compare our result. We will compare our result with one's experimental structure, the TEM picture. We found also the stacking fold is also spread entire nanograin, and also the deformation twin is found right in here. So it's kind of agreement with the experimental result. And also, if we look at the 3.2 strains close to the intersection, we see there's a lot of the shear transformation zone happens right in here. And later, there are some more atoms that are plastic deformed than the atoms in amorphous layer than the atoms in the crystalline layer that is plastic deformed. So there might be strain gradients across the intersection. So then, in order to quantify this strain gradient, we use slice analysis, where the structure is divided evenly into 12 slices from S1 to S12, and this picture actually is the nanonam structure rotated along the x direction for 90 degrees. And then we calculate each slice's average slip vectors value and mapped as a function of the slice's number. And we combine different strains together to form this average slip vectors map. It shows that before the dislocation emission, there's already a strain gradient across the intersection slices such as S2 and S3 and S10 at S11. So with the increasing of the strain, these strain gradients becoming more obvious, and even the crystalline interfacial slices become to be higher than its interior slices value. So what happened in this material? And let's look back into the snapshots. We found that there are more atoms involving in the STZ's deformation in the amorphous area than the atoms involving in the dislocation or grain boundary deformation in the nanocrystalline layer. So the plastic strain gradient indeed exists due to the disparate deformation mechanics. So how does this gradients related to the dislocation emission and absorption? Then we isolated one dislocation plane which only contains 2 layers of atoms. Then it shows that at 4% strain, there is this leading partial emitted from the grain boundary and the ACI intersection. And later, this leading to a stacking fold right here at 4.18% strain. The trailing partial actually is emitted from the nanospot, and removing this stacking fold to lead a full dislocation glide. And if we visualize through the slip vector analysis, we found that the first one is leading by STZs, triggered by STZs in this intersection, but the later one is triggered by another STZs in amorphous layer. And we applied the similar slice analysis to this study, and we found that at the string, when the leading partial is emitted, we already see the strain gradients as the upper interfaces slices S10, S11. And with the dislocation emission, the crystalline layer slices has been progressively elevated. And when it's being absorbed by the lower amorphic ACIs, the amorphous interfacial slices has been enhanced. So this showed that the slip vector analysis successfully captured the dislocation sweeping through the crystalline region. And then, in order to capture the instant change of this process, we normalize the upper amorphous crystalline interfaces and the lower amorphous crystalline interfaces slices value using the whole dislocation planes average to show as the change happening in here. So we see that before the dislocation emission, the amorphous upper ACI slice S11's value is already higher than the crystalline slices, and it's keep increasing, and it's experienced a drop right in here, which corresponding to the crystalline upper ACI's values peak. This actually is a dislocation emission process where the STZs trigger the dislocation emission right in here, and the same situation happened for the trailing partial emission. And then when the dislocation being propagate to the lower crystalline ACI slices, it shows that there's corresponding to a surge of the crystalline LACI's S3's value, and which later enhance the amorphous lower ACI's value. And this showing that absorption of the leading partial trigger the STZs in the lower amorphous layer. So, another point to mention here is like after the full dislocation glides through the dislocation plane, we think that the lower ACI STZ seems like linked by this full dislocation glide and leads to a shear localization in this area. And then we find if we inspect the planar view of the nanocrystalline layer, we find the biased dislocation activity observed in the upper corner and this lower corner. And this is coincidence with the shear banding forming in the amorphous layer. And all this shows that based on a quantitative analysis and a qualitative observation, shear banding and dislocation plasticity are coupled via the STZ initiate dislocation slip, which in turns to promote the strain localization in the amorphous layer. Then, as I said before, we're comparing the stress rate curve of the EQX nanocrystalline copper with the columnar one, and we said this difference when the strain being accommodated. So then we use the continual narrow deformation matrix grain strain to characterize different mechanics contribution to the overall plastic strain. And then we found out that this picture shows the columnar nanolaminate structures as the grain strain map, and it shows that plastic strain is initially accommodated in the amorphous layer, which take about 0.3%, 0.3 fraction of the total grain strain, and the grain boundary layer, which is about 0.2% fraction of the total grain strain. And this trigger the later dislocation activity in the crystalline layer. And then we show the EQX nanocrystalline copper. The significant difference between these two structures is that for the EQX nanocrystalline copper, there are more strain being accommodated by the grain boundary, almost like twice as the one in the columnar structure. So for the strain being accommodated by the grain boundary, such as the grain boundary dislocation emission and absorption, and the grain boundary sliding, grain boundary decohesion could lead to the void formation and ultimately leads to the poor ductility of the material. So if we replace some of the grain boundary with the amorphous crystalline interfaces, we might suppress the grain boundary deformation and might improve its tensile ductility. Then, as we know that the nanocrystalline metals failure through the initiation and the propagation and the coalescence of the nanovoid in the material, then we use the construct surface mesh to visualize and quantify the nanovoids and its volume fraction in the material. As shown in this map, at the 6% strain, there already are nanovoid forming in both columnar structure and the EQX structure. And later, at 11 strains, EQX nanocrystalline copper's growth rate actually changed to a fast pace, while for the columnar one, it's almost remain in a constant growth rate. And then at the last, the nanovoid fraction is more than double in the EQX nanocrystalline copper than when compared to the columnar one. And also, it's worth pointing out that for the single crystalline nanolaminate, it's remain constant 0, means there's no void forming in the single crystal nanolaminate. It shows that when we replace the grain boundary with the ACI, which shows the excellent tolerance to the damage, we can suppress the nanovoid formation and improve the material's tensile ductility. So to sum up today's point, we studied the unique mechanics in the columnar nanolaminate. The dislocation emission results from the grain boundary and ACI immediate process driven by the shear transmission zones activity, and absorption occur at ACI, which then leads to the localization of the shear strain in the amorphous layer, and ability of these defects to be absorbed at the ACI provide a means to circumvent nanowave formation and strain localization. So at last, I want to thank my advisor, Jason Travis, and I want to thank my coworker at the EMML, and also I want to thank IACS for providing the computational resources. And also, I want to thank our cooperator at the Brookhaven National Lab for providing also the computational resource. Thank you. So, any question? Yeah.
Very interesting. So, in your model of the grain structure,
yeah.
How sensitive are the results to the grains you choose, right? So the grains are chosen randomly. So if you
mean this one?
Yeah, right.
Yeah.
So if you use a different set of random grains, how do the results change? I mean,
so we actually all this result is coming from one simulation set because we want to correlate the structure with stress strain curve, and if you average this, there's going to be no correlation. And it's just like exchange is not so much. And for each grain size, it just changed a little bit with different, a little bit slight change in the yield strain and the flow stress, yield stress and flow stress. But we can have a good, reproduce of the result we have right here. And actually, for the grain size here, it's not a random orientation or random grain size. We modify this. We modify this because we use the Voronoi tessellation. You're going to have a really small, accurate angle between the two faces. And then when we impose a small separation distance between one Voronoi seed and another Voronoi seed, then we get rid of those really small and accurate angle in the material. So, and also it imposes a smallest grain size and have a really narrow grain size distribution. And also, because this is actually as a textured material, it's going to have a really small misorientation angle, which leads to a really small angle dislocation grain boundary. Then we use another Monte Carlo process to make the material, most of the grain boundary is the high angle grain boundary. So that's how I made this initial structure, and all the other structure is produced in the same way. So
how much of your time did it take to actually do all of that work?
It's take almost 1 year, and yeah. So the first is the fill atoms program. I just like fill this Voronoi tessellation with the atoms, and that actually is the I learned it from other people's dissertation, and it has a whole code. I have to learn it. Then I have to learn the Monte Carlo process to modify the structure, and it takes almost 1 year. And we want to get you want a couple result, and so you can have a confident result to present. So it takes a while. Yeah.
I'd like to emphasize that I was an experimentalist coming into Stony Brook, and had to start from pretty much square zero getting this together. And while I could help him on saying these physics are wrong, I was of no help to him in the coding world and doing anything else with coding on the Monte Carlo process. So there was a learning curve, and that's why I would say Ben is going to spend 5 years
Micrometer range is really hard for the
I
empty.
know you cannot calculate, but can you extrapolate any of the conclusions? How much this whole story depends on the size
Of the material.
nanometer size?
Yes, yes. So, so if we look at the first page, the Hall patch law. As this Hall patch law as is developed, I think in the 1950s, about we refine the grain size from the normal size, the micron size, to the ultrafine size, and all this is effective, or is true for the micron size to the ultrafine size, and only its deviation from the Hall patch is breakdown only after the grain size is smaller than the 10 to 20 nanometers. So I think the conclusion for the micron size is it's still the strength of the material still follow this Hall patch relationship. So, thank you.
So I guess a related question. So
Yeah.
the strain rate that you got, I mean, in a lot of atomic scale simulations, right, we have to do things faster.
Yeah, really fast.
In reality. So
Yeah.
How does the strain rate that you have compare with experiment?
So the strain rate I'm using in this solution is 10 to the 8 per second. It's really fast, and I think the strain rate is the
What are the units of that?
so the units. I think it's no units. Units.
It's actually meter per meter or nanometer per meter. It's a delta length scale over length scale, so it
But
becomes
there's a time in it? The rate's got to have a time in it.
The rate, yeah, so the strain rate it's per second, so it's actually second to the -1 is our strain rate.
10 to 8.
Yeah, it's really fast. Actually, the normal experimental is about I don't.
Orders of magnitude less. Usually quasi-static is
Yeah.
something like 10 to the -5.
Yeah, -5.
But with that said, I mean, this is a lot of these processes, these mechanisms are thermally activated. So it has a similar effect as reducing the temperature to really low temperatures because you're not giving a lot of these mechanisms time to occur. So, for example, dislocation, nucleation at grain boundaries, which is not found in classical Hall patch, but found in nanocrystalline metals, where you start to come up to this plateau of Hall patch strengthening. That's because the fundamental dislocation mechanisms shift to grain boundary mediated processes versus the classical dislocation interaction type mechanisms.
So, but the conclusions would definitely depend on temperature. So, what temperatures are you using for?
So the temperature is the room temperature, about 300 K. So that's the temperature we're using. But this a lot of dislocation activity is thermal activity. Some people using a really low temperature, like 10 K, to get rid of the the thermal activation process. But we choose to use the room temperature to simulate because we want to compare this to the experimental result a little bit. But so that's we choose the 300 K.
I'm going to ask you a question. So you don't know this, but I've been the last 2-3 days just working extensively on your manuscript on this, and
Yeah.
I have it open in front of me right now. The question that I'm interested in is in your results,
Mhm.
we see biased dislocation nucleation in these structures, often to grain boundary intersections with the amorphous crystalline interface.
Mhm.
Based on your analysis here, can you determine whether or not this has to do with some effect on the activation energy for dislocation nucleation at these various interfaces? You have 2 types of interfaces. Or do you believe that it's related to some other mechanism?
Let me go to that page first. So
So you highlight here something that's related to grain boundaries. I mean, you can see it all over here. You don't need to skim through anything. You highlight mechanisms that are related to, you see bias nucleation at grain boundaries. A lot of theory has discussed that this occurs because of a reduced activation energy. Stop going through.
okay.
Go back to your previous slide.
Okay.
So this occurs
thank you for your question. So I think let's talk about nanocrystalline first. So nanocrystalline material, the dislocation is emitted from the grain boundary. Actually, there's a couple theory. The theory from the one theory is talking about the strength concentration, which trigger the dislocation, and also another theory is about the free volume at the grain boundary and the triple junction, which actually they can migrate to the point and trigger the dislocation. So this could both happen in our nanolaminate structure. And we remember this point is that we have different kind of material combined together. So they're going to be some, I think, friction or sliding in the interfaces. This might lead to the strain concentration at the interfaces. So that is the next step I'm going to look into to see how the dislocation being activated in the interfaces. Another reason is if we look at the mechanical glasses, it's characterized by a lot of free volume. So that means the material is less dense than the crystalline form. There are going to be a more free volume in the amorphous layer, which could like migrate to the interfaces and then trigger the dislocation emission from there. So we can also use these two different views to study this interfacial dislocation emission process. I think that is.
Thank you. That's actually what I was hoping to say something along those lines. That opens up your next ladder.
Yeah.
Something that I think you overlooked here and that I'm seeing now is that you have two different events occurring here. You have one where the dislocation emits from a grain boundary ACI intersection.
Yeah.
That suggests that it has something to do with the fundamental shift in activation energy, whether it's stress concentration induced or induced by some other mechanism. When you look to the trailing partial, that little red dot for everyone, where the trailing partial is emitted, that does not occur at the same point.
Yeah.
Both cases, it occurs where you have high atomic slip at that interface,
Yes.
which I believe is occurring due to a strain transfer process between shear transformation zones being activated and what you have, your dislocations being nucleated into the crystalline layer, which suggests that it's actually more of a free volume type of argument.
Yeah.
Although you can't rule out stress concentrations, because if you have a shear transformation zone activated at that interface, which results in that interface shearing, that will create a stress concentration and kick a dislocation out.
Yeah.
So we're going to be able to allude to this in our active paper, but a detailed analysis of stress fields, local stress fields, free volume, in just this one slide will answer that question.
Yeah, that's
you have two different events occurring here.
Yes, that's a really good perspective to study. Yeah. Okay.
Well, I have a question because you talk about mainly about the upper ACI and lower ACI, but I remember when you make the columnar nanocrystalline, you also have the ACI that is vertical to those upper and lower.
That is not ACI, that's grain boundary.
That's grain boundary, but it's amorphous. But what is the thickness of this amorphous?
So some people say the grain boundary is actually amorphous, but there's there's controversial about what the real grain boundary is. I believe the grain boundary is not amorphous layer. It is actually a result of different grain have different orientation. So they meet together, so it's creating a misorientation at the interfaces, and this leads to a grain boundary. And usually there are different kinds of the grain boundary. So the one with a larger misorientation angle is a high angle grain boundary. Its layer gonna be a little bit thicker because you have a lot of free volume in the grain boundary. However, when you have a really closed configuration, you might only have some dislocation core at the intersection, and other is connected. So that actually you cannot measure its thickness. But amorphous layer is usually much thicker than the grain boundary.
So do they make a difference during the
Yes, of course, they make a difference. So, so the dislocation triggered by the amorphous and grain amorphous is the next step I want to study. I still don't know yet. But the grain boundary, actually, I talked about this for just minutes ago. It's actually some is related to the stress concentration, and some is related to the free volume migration. So that's two types of the result, the dislocation being emitted at the grain boundary. So yes.
So you did a lot of these studies using labs. So can you talk a bit about the calculations? How much computer time? Did you use MTI? I mean.
Yeah. So my structure, this structure actually is 10 nanometer structure. It's about 2 million atoms. So I use a strain rate, actually 10 to the 8 per second is actually a slow strain rate in the computational. Normally this one I use. Yeah, so this typical takes for the whole run, I think it takes too long, too long quick, or the 96 hours. We're using the each run using the 192 cores. So each is a little bit slow. And if with even larger one, I cannot finish in the single cell. I have to restart a couple times. So yeah, the structure is really large for the simulation. It's rather than the force principle is much a smaller one. Yeah.
The general rule is molecular dynamics is as good as potentials are good. So with 2 million atoms that you're using, you must have quite primitive potentials.
Yeah.
So how would you change the results with varying different potentials? Or have you, what was the criterion for choice of the potential that you have done? And how you know that it is a good one?
So the potential I choose actually is first is widely used. I see another paper using this potential, and the second is the experimental composition of the copper-zirconium ratio is actually 3:1, and I choose this is copper 64 to the zirconium 36. And I choose this composition in my structure, and it is closer to the experimental data. And I want to use this composition, which is, and all the potential is using this composition too. So I make a like agreement with a potentials composition. And then also this is close to the experimental composition. So that's why I choose this one. Another one I'm going to try, but it's copper 50, the zirconium 15 potential. It's changed the composition of that potential. It's going to change a little bit of the result. But I'm going to try another potential to do this work later.
Yeah, so the validation with experiment is then crucial for such this decision or for, let's say, certainty of your results.
Yeah. Yeah.
And so that must be followed soon, yeah?
Yeah. I just want to, our computational structures composition is really, it's not exactly at the experimental, but it has a copper-rich one. So that is close to the experimental. So that's my choice of the potential.
So you should be aware that there's more behind that selection.
Yeah.
The potentials that you have, if you go through all the papers, have been experimentally validated to show that they can reproduce specific things that we care about. Things like stacking fault energies, the relationship between stacking fault and stable and unstable stacking fault energies through the generalized planar fault energy curves. So these are all important aspects for reproducing what would be more realistic in terms of mechanisms that have to do with these interfaces, that all of the interfacial properties, energy specifically, are recreated by use of these various potentials.
Yes.
measure certain aspects that these potentials can produce and compare that with experiment.
Yes. Thank you. So, one more question?
Wasn't it enough?
It's enough for me. Okay. So I think there's going to be a pizza and a freshman outside, right? Inside.
That's good. Thank you.
Yeah. Thank you for coming to my colloquium.